Hey everybody, this is Jim Neve from Jim Neve Woodworks again. Today I want to do a video about tuning the acceleration and some other parameters in Mach4 to get better performance from a cut perspective, as well as reducing the vibrations in the machine that will cause laser lines to be kind of squiggly or see little chatter marks in your V carving, as well as to save some wear and tear on your machine. Acceleration is hard on a machine. It's no different than, every time you go to an intersection, slamming on the brakes and then flooring it when the light turns green. That's just hard on the drivetrain and your tires and your brakes. It's the same thing here. It wears out gears faster, shakes bolts loose and things like that. So there's a trade-off between getting the job done quickly and then not making the wear and tear on your machine any worse, and then getting good performance. And there's a lot of difference between your types of work. If you're somebody that's cutting large 4x8 sheets of plywood all day long for kitchen cabinets, you care about speed, and you're not really caring too much about cut quality, and you're not making a lot of corners. You're just making straight lines, maybe drilling holes and stuff like that. So there you can run very high accelerations and speeds and not really have to worry about wearing the machine out as much, or shaking the machine so much that your cut quality is poor. However, if you're doing really fine work like this, where in this case there's no straight lines in this, most of the lines are less than a quarter of an inch. Most of the vectors are very short, and so the machine is constantly stopping and turning and going the other direction. If you use the default 50 inches per second squared acceleration settings that comes with the AVID machine, it's going to shake violently. You're going to get a lot of oscillations in your cuts. The quality is not going to be good. If you're doing that when you're doing things like 3D carving, this again is the bit is everything's slowing down and going up and down and starting and stopping a lot. That causes the whole machine to shake, and you'll get little divots with these tiny bits. If you're doing V carving with a big V bit, you'll see the little chatter marks on the side from the machine shaking around, and especially if you use like a gloss finish on that, it's pretty noticeable. It doesn't look very good. So I do more fine work like this, and so I've been tuning my machine, trying to find out where's the best trade-off between, I don't want to run too slow, but I want good quality in my work. So I'm going to go through all the parameters, how to change them in Mach4, and how to analyze for your situation what might be the right answer. I'm not going to tell you what the right answer is for your situation, but I'm going to try to give you some examples of different types of jobs or tool paths, where some of them are long straight ones versus very short choppy ones, and you can see the execution time difference as well as the performance difference. One of my favorite ways to check for vibrations is with the laser, because it draws a nice thin line, and if there's any vibration in any axis, you could see it very clearly, and you can tell exactly which axis has that vibration. So it really helps you tune it down. So I'm gonna show some examples there. So if you have any questions, take a look at this. Put your questions or comments in the comment section below, and I always answer them. And if you have any follow-up you'd like me to do, I probably can do another video or do some experiments to try answer some other questions if I don't know the answer right off the top of my head. Okay, here I want to just kind of show the difference with that acceleration makes it. It's pretty obvious when you do jogging, you really get the idea. So I have my jog rate, or my max jog rate is 1,000 inches per minute, and my standard jog rate that's been adjusted down from the maximum in the motor settings. That's done on the Mach4 screen That's set at 500, so I'm at 50%. So what I've done here is I've set my X motor at 5 inches per minute, or sorry, 5 inches per second squared in acceleration, and the Y direction is at 50 inches per second squared, so 10 times higher. So you can see if I go, that's 500. If I do 1,000, sorry, my normal jog is 200, but my max is 1,000. So you can see it's very fast. Ramps right up. This also shows the value of having your soft limit set correctly too, because when you're jogging this fast, soft limits will ease you in and make sure you don't slam into the end. So you can see I'm holding the button on all the way and it goes down nicely. Okay, now we'll do the X direction. You can see that it takes almost half of the gantry to get up to the speed that is its maximum, and then it starts slowing down halfway just because it knows it's going to the end and needs to slow down. So you can't even get close to 1,000 inches per minute in the whole travel of the gantry end to end at that slow acceleration. See, now it'll start slowing down 2 feet from the end because it has to make sure it's not going to slam into the end. And if I do that without the fast and I just do 200 inches per minute, you can see even at only 200 inches per minute, it takes 1 or 2 inches of travel just to get up to speed. And versus the other direction, it's almost instantaneous for the 200 inches per minute jog, and still very short even for the 1,000 inch per minute jog. So that gives you an idea. Is in 4 feet I can't even get up to 1,000 inches per minute with 5 inches per second squared acceleration. So you can see how with the acceleration, your maximum speed can actually be limited by acceleration, because it depends a lot on how much time do you have to get up to speed and to get down to speed at the end of the vector 2. So we're going to see in a lot of my examples that at lower acceleration rates, the programmed feed rate is irrelevant because it's capped out by the max acceleration. All right, the first reason we want to do some tuning here is because the actual vibration it can cause the quality of the cut, or in this case the laser lines, to degrade. So what I've got here, I have a standard G-code file that I run to focus my lasers. So this basically walks across the Z0 location from -25 to +25 thousandths, raising the Z height. That's why the lines are different lengths, is because the focus point is changing. But this test is a good one to show the vibration problem. So in this file, it runs these numbers on the 2 axes at 20 inches per minute, and it runs the lines at 40 inches per minute. So it's pretty shaky over here on the left side. This is running the 50 inch per second squared acceleration numbers, and on the right here I'm running it down at 10. All the other parameters are the same. It's the same exact file. I've just changed the acceleration numbers, and you can see what happens is it starts out in the bottom here, bottom left line, and it's has a rapid movement up to this point in the Y direction, and then it's got some waves to it that you can see right at the beginning here, and they settle out as it goes across, and then it does a rapid movement again up to the new line, and then does a feed move to the left. And you can see every time it goes up across and steps up,
that first, these are about a ½ inch long. So this is about less than a quarter of an inch of waviness, but it every time it steps up, it has some vibration left in the Y direction. You can see it does not do that when I'm drawing lines in the Y direction. So in other words, the X direction rapid moves don't cause that problem. And if you look at my gantry, it makes sense. It's big and heavy, and there's a lot more weight that has to move, and there's 2 motors and everything, so it moves pretty hard in the Y direction versus the X is just sliding along the gantry instead of moving the gantry. And it's probably just more rigid in that direction as well. But you can see that, you know, there's a marked difference between the beginning and the end of each one of the lines. And when you go over to the right here and step down the acceleration, there isn't any of that. It's totally gone, and you can see how clear the numbers are written now compared to over here where they're all shaky, and that's because those numbers, they're only about 20 thousandths of an inch high. These lines are spaced at 10 thousandths. So there's a lot of small, tiny movements in there, so the acceleration is a factor in writing these numbers, and you can see the performance is much better down here. You can also see that the runtime for the fast acceleration is 93 seconds, but it slows down, goes up to 110 seconds when the acceleration is reduced. And that's not because of the portion of the G code that's running the lines, it's the portion that's running these letters. We'll see later, I have a bunch of tests to show just what the impact is to the runtime of acceleration changes for these small types of things, and I'll show that it really doesn't matter for these long kinds of vectors. If they're long and straight, the acceleration really isn't a factor at all. The other thing to note here probably is that if you're trying to build a good laser system that really needs low vibration and faster performance, a large CNC router platform is not the way to do it. However, I only have room in my shop for one tool, so I use it for spindle and laser work, and that's just, you know, a fact I have to live with. I've spent a lot of time trying to make the table itself more rigid, you know, and you can only take that so far. Most of these vibrations that are left are in the gantry itself, and there's no amount of stiffness in the table itself that's going to fix that. This is just the flexing and stretching in the gantry. So here's the second reason why too aggressive an acceleration in some cases is bad. This is a video I'm going to turn on here in a second of my whole spindle laser gantry area running a tool path that we'll show a little bit later that's very fine text. I use it kind of as a vibration test. It's actually, I wrote it small and intentionally to kind of test out different acceleration values to tune this. And this is running at the 50 inches per second squared setting that comes stock with the AVIDs, and only 40 inches per minute feed rate. It's not actually getting anywhere close to 40 inches per minute. That we'll see. Well, it's getting close, but it's not probably exceeding that by much. But when I turn this on, what we're going to see is even though it's moving a very small distance, it's shaking pretty violently. I mean, you can hear and see the gears turning. It's kind of shaking the whole machine apart. I don't like the extra wear that this is going to apply to my rack and pinion gears. And as I just showed before, this is causing pretty poor quality of marking with the laser and stuff. But you know, my whole tabletop is shaking around here, and this tabletop is optimized just about as much as I can, as I showed in my previous video about 1.5 years ago, where I put a lot of extra bracing in and everything to try and stabilize the legs of the whole table. But in the end, you can only do so much with that because the whole gantry itself can flex pretty significantly. There's a lot of mass here moving around. So with these big NEMA 34 motors, this whole head can shake around a lot. So that's what we're trying to avoid, is this kind of vibration that can damage the machine as well as cause poor quality cuts or lasering. All right, now I want to just kind of take a quick tour through Mach4 and show you where all these settings that we're going to talk about are and how you make the changes. We're going to talk about what, why the values that you pick need to be the way they are, or how to test out what the value should be later. But for now, I just want to show where all these settings are. So first, to make setting changes in the configuration, you need to make sure that the state of Mach4 is disabled. So I'm disabled here. So I'm going to go into configure and control the motor. We're going to look at the motor settings first. So if we go into control and go into the motors tab, you'll see these are empty right now because I haven't selected a motor. So we'll go up here and pick motor 0. Now I know this is motor 0 is my x-axis, but if you don't know or you've forgotten, just go over to the axis mapping tab here and you'll see which axis and basically the linkage between the motors and the axis, and you'll see that X has one motor, but the Y on an AVID machine has 2 motors. That's the one on each side. And I always remember to make sure that for that Y-axis you make the same changes to when you do make changes, make sure you change motor 1 and motor 3 to always be the same values. You want those moving together at the same time always. Now the other thing to remember is for most of this tuning, the Z-axis isn't really a problem. It really can't move fast enough, and it's a ball screw. Because it's a ball screw mostly, it just can't move fast enough and doesn't have enough mass there to really cause a lot of vibration and problems. So and in a lot of tool paths, you're not doing a lot of quick changes there. So mostly you're going to be using the X and Y in this tuning parameters. So anyway, motor 0s are X and Y is 1 and 3. So we're going to go back to motors here. I got my X-axis selected, and I talked about this in some of my other videos when we did how to do calibration for backlash, which is here, and accuracy of the travel, which is the counts per unit. Excuse me. So that was in the other videos. We're not going to talk about those, but the two main ones we're concerned about here are velocity units and acceleration units. So velocity is this is the fastest that Mach4 will let you move the machine for this axis. So this is 1001 inches per minute in my machine, because I use inches, so units are inches. So that means I can't do a feed move, a rapid move, or a jog move faster than 1000 inches per minute. Then the next one here that we care about is acceleration. So as we talked about, that's in your units, which in my case again is inches, and then seconds squared. So to make a change in these, you can just simply type over it, put 500 in here. Maybe I want, and you see as soon as you put that in there, the max value, which is this flat line here, changes to 500. Then I can change the acceleration. I got 30 inches per second square. Let's just change it to 10. When I hit return, you watch this line here. This is the rate of change, and that's why it has a slope on it, in time, in seconds, and then in magnitude of velocity here. So when I hit return, I guess you have to hit apply for that one. So for some reason, the scale changes immediately when you hit velocity, but you actually have to apply it to get the acceleration to change. But now you see it's a much more gradual slope, and I could change this to 5 and hit apply again, and now it's very slow. So this is how you can see what this is, and you can also see from this graph how long does it take to go from max. So each one of these is 1 second, these graduations in the time. So if I want to go from 0 to 500 inches per minute, you can see it's 1 and about to here. So it's maybe 1 3/4 or 1 2/3 or so. You can do the math to get the exact number, but that's the amount of time that it'll take to get up to speed, and then over here down, and it's symmetrical, so it's always going to be the same on both sides. Now you have to hit apply to make it to go through. If I were to change this to 10 and change this to back to 1001 and then go to my next motor and then go back, it will still be here on the screen, but when you exit, it won't have saved it. So you need to get in the habit of hitting apply on all your motors as you go through these, so that when you hit OK and exit out, it actually saves them all. This might have changed on some of the newer Mach4 releases. I haven't tested it out, but in general, in the past, if you went from one motor to the next and didn't hit apply as you went through here, you would lose your settings, and it would be kind of confusing. So always select the motor, make your changes, hit apply, then go to your next motor, make your changes, hit apply, and when you're all done, you can just exit. So that's how you make your changes to acceleration. And now a couple things to talk about. As I said, that speed number, first of all, the acceleration applies to all three: jog, rapid, and feed rate. Any movement for a particular motor, the acceleration setting for that motor will affect. So you can get annoyingly slow jogs or difficult jogs because they take so long to ramp up and down. It's very hard to make quick, precise jogs. So this is kind of the trade-off with acceleration. However, the max velocity setting in there, that's the maximum, but you can adjust feed rate, rapid rate, and jog rate right here on your screen. So that's why I have mine set at 1,000, because I want to be able to adjust up to that when I need to. The feed rate itself, I typically, of course, is set in the toolpath or the G-code file, but you can also modify it here just clicking up. So in this case, I'll be running exactly twice as fast as every commanded speed in the toolpath. I can also change my rapids, and I typically leave my rapid rate at around 500 here, or it's actually 50% of that max value. So these percentages, this percentage on feed rate applies to what's in the G code. The jog and the rapid rate are actually percentages of what's in the motor menu for max speed. So here we've got, and this is where it's kind of helpful to make sure that all your motors are the same number, because then this gets a little confusing as to, okay, I say 50% on the rapid. If I have a different rate for my for one motor versus the other, then I can get actually different speeds on different axes, and then these aren't necessarily correct for that. So I always set my X and Y to the same speed, and that way I know that the value here in commanded is the same. Now the command here will come out if you're jogging, you'll get the right speed because if you're jogging one axis at a time, this command part will come out right. But or I'm sorry, not command, the current, because the current here is displaying whether you're feeding rapid or jogging. But so you can adjust these on the fly. That again, I keep my jog rate to kind of a smaller number so I can move nicely without like slamming my Z down into the table. If it, so I don't really want the jog rate to be too fast. Okay, now something else that we're going to want to change is the constant velocity, and we're going to talk about that last. It's kind of the final thing that we want to do after we've figured out, well, what acceleration is kind of the best value for us. So if you go into wizards, we'll select a wizard, and there's two wizards we're gonna want to use. One is called MCCV tuning, that's constant velocity tuning, and the other one is CV feed rate. The CV feed rate is simply kind of a display of the data that the tuning wizard creates, and we'll talk about how these are used by the software later. But you basically have two tables. This data is stored in your machine INI file, but it's created by the tuning wizard, and you get a blend radius value for every angle from 0 to 180 degrees. If we go all the way to the bottom, or I should say 0 to 179. So we have 180 entries into this. This is just, again, this is a display to see what's generated. You can also just simply open the machine INI file and see this. And then the other wizard is the tuning wizard, which was this one when we open that. And we'll go through what this does again later. And then the final thing is to see where we turn on the constant velocity mode, and that is again back up in the configuration for Mach4. Right in the very first tab, defaults, you get a motion mode here, constant velocity and exact stop. So I'm not going to cover what these do yet until we get to the constant velocity section. But anyway, that's all the areas of the software that we're going to be playing with. So when I say, go change your motor acceleration or max speed, you know where this is. So there is one other thing too, that besides some of these can actually be controlled in the G code. So for example, constant velocity or exact stop can be overridden in your G code. Constant velocity is set with a G64, and exact stop mode can be created with a G61. And you can see that back down here. It's actually in G61 mode. I'll close this. Because I haven't enabled the machine yet, I can't. I'm in simulate mode, so I can't change. Well, actually, it reran it. So when you enable your machine, it reads in those settings from the tabs, and you can see now it switched to G64. So it actually picked out the value from the machine INI file and loaded it, and so this. I'm in the constant velocity mode now so this is a good place to check, does yours say G64 or G61? So anyway, that's all the software settings to enable the things that we're going to talk about next. So before we get too far with testing out different acceleration factors and going through the software settings that achieve that and everything, we need to cover some basic terms of what we're doing here. This is really just basic physics, but we have a few terms, and then I'll just do an example here of what that means. So the mass, when we talk about how much mass there is of the gantry and stuff, that's the amount of matter that the motors have to move around. So for your Y direction, those two motors have to move the whole gantry back and forth, as well as everything on the Z stage and the spindle and lasers and whatever else you have mounted on there. So that has to move more mass around than, say, the X-axis, which only has to move the Z stage and everything mounted to it left and right. And so that's why part of the reason why there's two motors on the Y, as well as the two motors are used to square up the gantry as well. But more mass needs either more motor or bigger motors if you want to get higher accelerations, because it's got a harder job of moving the mass around if you want higher speeds, or sorry, higher accelerations. The speed is just the rate of movement across the direction. So it's measured in inches per minute or millimeters per second, or however you want it, but it's distance over time. Acceleration is the rate of change of that speed. So inches per second, or in other words, inches per second squared, is the units that I use. You could have millimeters per second squared if you're using the millimeter units in Mach4. But this is how fast are you increasing or decreasing the speed as you're starting up or slowing down to make a turn from one vector to the other, for example. And then we have oscillations. This is the actual ringing of the machine components when they're disturbed by a momentary force. So if you think about, you can just smack the gantry on the side and it would oscillate a little bit. But what we're really talking about in this discussion is the force that's applied from the motors against the mass to achieve the acceleration setting you have programmed. It has to apply a force to that mass, and it's going to do it for just a certain amount of time. Once you've achieved the acceleration, then the force that's left is not accelerating force. It's just the force that's needed to push the bit through the material if you're using a spindle, plus any friction like for the bearings and stuff. So you still have a constant force for cutting, but the extra piece for acceleration is gone. And this acceleration time is momentary. The less the mass is, or the higher your acceleration setting is, the shorter that time will be. The mass actually probably doesn't affect it that much, at least on a stepper motor, because the assumption here is that we're not losing steps, so we're not pushing the motor so hard that it'll lose steps. So the rate of the acceleration value is actually set by the setting in Mach4, and the controller is simply speeding up the pulses that it's sending out to achieve the acceleration rate that you've programmed. So the mass doesn't come into the acceleration rate so much as, but it certainly affects what the oscillation looks like. And once that momentary force is applied, things will bend and move around a little bit, and sometimes it's very minimal, and sometimes it could ring for, I've seen like 3 or 4 oscillations quite often on some of my laser marks. So it just depends on the rigidity and the different characteristics of the mechanical system that's being disturbed, as to how long it lasts and the amplitude of that and everything. So if we have an example here, let's say we want to move our gantry 900 to up to 900 inches per minute feed rate. So we have our feed rate programmed to 900 inches per minute, and at some point it's going to start at 0. It's going to be stationary, and then it's going to ramp up to 900 inches per minute, and then at some point it's going to get done with that vector, and it's going to ramp down to 0 inches per minute and stop. So if we have our feed rate programmed to 900 inches per minute, and we have Mach 4 motor settings, which we'll go over that in a bit, where those are in the software, set to 10 inches per second squared, that's equivalent to 600 inches per minute per second. So in other words, the inches per minute part is the velocity, and we're changing that every second, that amount. So what that means is, again, assuming that we're going to make this assumption the whole time that we're not pushing the steppers so hard that they're losing steps, so they're able to apply enough force to achieve the acceleration that the motor drivers and stuff are pushing out to them. So that would be 900 inches per minute velocity divided by 600 inches per minute per second rate of change, which is our acceleration. That means it's going to take exactly 1.5 seconds to go from 0 to 900, or from 900 to 0. So we can see from this example that the ramp up and ramp down time can be very significant. 1.5 seconds just for something going 900 inches per minute. So that that could be quite a few inches in distance that it's ramping up and ramping down on a tool path. So there's a lot of kinds of tool paths that you would never get up to speed, and the acceleration actually becomes the limiting factor for speed. In many cases, it'll never reach the full speed, and at some point the programmed feed rate becomes irrelevant, and it's all about the acceleration. And then there's other kinds of tool paths where they're long, like for maybe you're cutting out cabinet parts and they're multiple feet long, and don't have a lot of corners and stuff. It's just a lot of straight lines. In that case, the acceleration is almost meaningless, and it's all about the feed rate. So I want to give a couple examples of that. So let's go ahead and look at this. On the left, I plotted two different accelerations here, 10 inches per second squared and 50 inches per second squared, and ran this tool path at multiple different feed rates here. So 6, 15, 25, 60, 90, and 120 inches per minute. And the tool path itself looks like this. In fact, this literally is the tool path that I burned it in with the laser. This is a 1 inch on a side square here, just to give you an idea of the scale of this. So these letters are probably on the order of 100,000ths of an inch tall is all. And this, so it's very, very small text. It's actually 2-line text even. So hardly any time to ramp up and ramp down here. So if we look at this at 10 inches per second, this basically says that it's somewhere around 30 inches per minute. The toolpath is totally limited by the acceleration time. So the execution time here is the y-axis. So you can see that at 10 inches per second, it will speed up if you run, or it'll actually start to slow down, I should say, if you run below this point here. So below 30 inches per minute, then the feed rate will affect the execution time. But trying to run faster than 30 inches per minute has zero effect on the execution time. And that's, again, because there's not enough acceleration programmed here to get any of the parts moving up to the program speed. So it literally is flatlined past that point. And now you can see with the 50 inch per second squared, this orange line, that point happens at about 50 inches per minute. So this is a case here where this tool path just simply is not going to run any faster, no matter what you program for feed rate once you get past these points. Now here on the right, I have a different toolpath. This is just a 3-inch square that I ran 3 passes on. So it's just going around the square 3 times. And you can see that this feed rate line never flattens, or sorry, the execution time versus feed rate never flattens out. In other words, it's and that there's no difference at all other than 2 seconds. There's a 2-second difference that's constant between the 10 inches per second squared and 50 inches per second squared. So it's almost independent of acceleration, except for the reason the 2 seconds are there is this toolpath actually has about 6 or 8 inches of rapid move at the beginning and at the end when it's coming from and going back to the safe spot or safe location. And that is a rapid move, and it's 500 inches per minute. So it's a very fast rapid move. So there's a couple seconds worth or a few seconds worth of travel time to and from the safe location, and the feed rate isn't used for rapids, but the acceleration does apply to all movements. So there's the acceleration speeds up that time when you go to 50 inches per minute. So, but you can see it's constant for feed rate, and that's because it doesn't use the program feed rate for that rapid. It's a flat 500 inches per second. So it makes a constant 2 seconds different. But you can see for the overall, the rest of the toolpath, which is feed moves, it is 100% dependent on feed rate. So here's your kind of 2 examples of how you go from really short moves to toolpaths where you have really long moves with few corners. You can be completely feed rate dependent or completely acceleration dependent. And you can also kind of imagine that video that I showed with all that shaking, that also kind of is going to disappear on something like this long toolpath because there's not very many direction changes. So there's only 4 of them per turn around that square, and they happen real quick, and it's over. Whereas you can kind of imagine the small text here, it's just in a constant direction change. I mean, there's no straight lines in here that matter. It's all direction changes, constantly doing it. So those are your 2 extremes, and that's why it really matters what kind of work you do. I mean, these AVIDs are very flexible machines, as most CNC routers are. And if you're somebody doing cabinet work and putting 4x8 sheets of panels on there and of plywood and cutting them out all day long, vibration probably is the least of your concern. You just want to run fast and get the job done. But if you're somebody that does laser work, V carving, or any kind of intricate work with these smaller tool paths, the vibration can become a factor both for machine wear out as well as certainly for the quality of the work that you're getting out of the machine. All right, another kind of tool path that I was interested in seeing what the impact of the acceleration was for something like this 3D carving here. I did this one last week. Across the center here is a very jagged or has a high depth part of the carving where it's going up and down probably 3/4 of an inch at least. So in that case, there ought to be a lot more starting and stopping and slowing down action, whereas up on the top in this red slice, it's a lot more smooth and very subtle bumps. So I wanted to run the 2 different acceleration settings across these 2 and see what the difference was. So the feed rate was actually 120 inches per minute, and I'm comparing both of these locations at 10 and 20 inch per second squared. So the blue slice in the middle, the jagged one, There was about a 20% difference in execution time with the obviously the 10 inches per second squared being slower, and the red only an 8% difference. And so this again is where you can look at it and say, well, what kind of carving am I doing? Does it matter whether or not I have a higher, slower acceleration? How much does it matter for execution time? How much does it have for vibration? I could tell on this one, I didn't measure it, but I could tell from the noise and just feeling the vibration of the tabletop that, you know, the blue had more vibration doing this at 20 versus 10, but it wasn't significant. On the red, I couldn't tell the difference from a vibration standpoint. So again, you can kind of gauge this by what kind of carving you are doing. In the case of this whole thing, you know, if you use the information from this slice, you'd see, well, a 20% difference is significant. This whole carving, I think, took 9 hours to run or something like that. So, you know, that'd be an hour and a half difference. But the reality is that half or more of this carving is actually pretty smooth. And so if you weighted this whole thing between the rough and the smooth areas, it's probably more like a 10% difference or possibly even less, just because the majority of this is smoother. And so it would be more like the red area with not as significant of difference in between it. So for me, I would probably just run 15 inches per second square, just kind of in between these 2 points. Well, now I've kind of isolated the range down to somewhere between 10 and 20 inches per second squared as the area where I probably want to have my machine set at most of the time, based on some of the other testing I've done. And so I kind of want to see, well, where is the fine line there? I don't want to go below 10 because I know that all of my noticeable vibration in my cuts and in my laser marks are gone by then. And anything below 10 starts to become kind of annoying for jogging, because it becomes significantly noticeable when you're just trying to jog around. It ramps up and down too slow. Anything more than 20 I know has a lot more vibration and really shakes the machine. But somewhere in this range, between 10 and 20 seems to be good. So I did a quick test here, again using the toolpath that has the small text to gauge the vibration, as well as a small laser marked 1/2 inch square to also visibly see the vibration. So what I on the top here is 20 inches per second. So when I draw a square here at 60 inches per minute feed rate and 20 inch per second acceleration, inch per second squared, I still see some little sine waves down here in the ends after it turns a corner. Again, I only see them on my Y direction or in line with my x-axis here, because of the nature of the way my gantry likes to oscillate. But it's still there. I don't really want that. And when I take this is basically a vibration meter on my phone that uses the accelerometer in the phone, and it's like a 2.75 average reading on here. And this is the units here are probably not as important as it is just as a relative gauge. So I'm going to compare all three of these. So at 15 inches per second squared, now I have clean corners. My oscillations are gone. My vibration has dropped down to an average of 2.5 on this scale. And then at 10 inches per second squared, it's obviously also clean. And my vibration's still at 2.5. So it's not getting any significantly better than 15. So there's no point in going to 10 in my mind. 15 is kind of where I get the best performance. So from the previous test, I already know I'm going to lose execution times, speed on many of my tool paths that have these really short, small vectors. So I don't want to go any lower than I have to. So from this, I'm kind of settling in on 15 inches per second squared as kind of my standard value that I'm going to set my Mach4 motor menus to. Now, I don't have any tests in here for laser rastering. Then the reason is that's a very different case. In that case, I can actually make an argument for setting it much higher, and I'm going to do a separate video on that. There's some new laser features coming out in the near future for the ESS, and I'm going to cover all the acceleration settings along with the other pixel fine tuning and everything. So I've left that out here because it's kind of a unique case as well. Now, one final thing we need to talk about, because we're messing with acceleration settings of the motors, is constant velocity mode. This is a mode that Mach4 has. It's also other CNC controllers have it. The whole point of this is to try and maintain the velocity or feed rate as close as possible to program values while it's doing things like complicated corners and stuff. The alternative to constant velocity is full stop mode, which basically, if you imagine this square here, it's got four vectors where it accelerates up to a speed, runs across here and decelerates down, stops completely, then starts up in another direction and keeps doing that. So it's starting and stopping all the way around it'll make the squares perfect. But what happens is that stops. And so if you've got a spindle that's spinning, you're not maintaining your chip load. And that's very important for metal cutting. And in some cases, it's very important for lasers. If you've seen laser action where you've got big burn spots in the corners, that's because either there isn't a good CV mode, or because the laser controller section can't scale the PWM or the power value of the laser as it slows down. So for cutting and for lasering, you want to maintain that so that you don't slow down, stop, and sit there with the spindle spinning at full speed and burn the wood, or in some cases you overheat the cutting tool on metal, and it can make anytime there's a major change in speed like that, it can change the load, and you'll get like little marks from that. So the idea is to hold the speed up as much as possible. Now, what we're going to see here is that it's really not that much of an issue on the AVID machine, at least with the NEMA 34 motors, because the acceleration values, even at the low values that I'm picking, really are still relatively fast, and this mode doesn't really do much. But I'm going to go through it anyway so everybody understands it, because I haven't found a lot of good explanation out there on what CV is and how it works. So I'm going to go through that just to get some coverage on this. So again, it's to help the quality of cut. On the ESS, it's not really needed for lasering because the laser can scale power properly. I'll show that. There's a wizard. Essentially what this mode does is you run a wizard and it asks a question: which motors do you want to look at the acceleration on? So what you do is you set your motor acceleration that you want to use. So in my case, I've kind of determined now that I want to use 15 inches per second squared. So I'll set my X and Y motors to that value. Then you pull this wizard up and you're going to tell it what the error tolerance is. And what that error tolerance is the distance between this corner and a radius that the wizard's going to determine. And so if I say 1/1000th of an inch is the biggest error I want, then it's going to create a radius for this 90-degree corner that allows it to have no more than 1/1000th of an inch error between a radius circle there and a true square. And what that does is it calculates that radius, it's called the blend radius, calculates that for that given error on every angle between 1 or 0 and 179 degrees. So this, I cut this table out here. This is a snippet out of the table. There's a MCCV feed rate wizard in Mach4 that after you run the wizard to create this data, this basically shows you what it is. So for this 90-degree square corner, it's saying the blend radius is 2.7 thousandths, which that's the radius of this circle. And the feed rate is allowed to be up to 16 inches per minute on that corner, given the acceleration settings of 15 inches per second square. Now these are worst case numbers. You actually have to run a lot slower than this to make anything noticeable. So I did a little experiment down here where I made this square. I put a huge number in. I put 2 thousandths or 200 thousandths of an error. So 0.2 inch I allowed in the wizard, which is a very large number. You would never do that. Running 40 inches per minute and a very slow, Andrew at Warp 9 calls this school bus mode because the acceleration is so slow, it's like a school bus, of 5 inches per second. I had to slow it down or set the acceleration that low before it was even noticeable. So you can see here, I ran the square is with constant velocity mode turned off, and you can see it makes a perfect square all the way around. And this doesn't have a rounded edge down here when the CV is turned on because this is where the square starts and stops. So it's not actually going around the corner. So that's why only these three have the rounded when I turn CV on. So when I turn CV on, it followed the same path until it got to that radius, and it basically makes a little bit of a shortcut so that it can smoothly run around that corner. So what it's saying is this corner is not going to be more than 200 thousandths, which it's not anywhere close to that. It's actually much smaller than what I put in for this, and it cannot run more than 16 inches per second, or inches per minute, sorry, around that corner. Typically what I've seen is that it can get away with a lot less, just because these I think this mode is really made for big heavy machines that don't have very big motors. Maybe with the NEMA 17s or 23s, this would be a useful mode. But from what I've seen, I can't tell any difference between CV mode or not. And I kind of proved that with this data as I did that same square. I ran these at 60 inches per minute, I believe, but I did two different accelerations. I did the very fast stock one, a 50 inch per second squared, and a safe one that should be clean on this machine at 10 inches per second squared. And I did both of those with the constant velocity off and both with the constant velocity on. And you can see that with on or off at the high speed, I've got these little ripples in the Y direction, just like always. And they're no different. CV didn't help or anything. And then with 10 inches per second squared accelerations, I don't have any ripples on either one, CV on or off. So for the range that we're talking about here, CV really doesn't do anything. You're gonna get nice tight corners either way. It's not really kicking in, from what I can tell, until you run well under 10 inches per second squared acceleration. So my advice on this one is to figure out what accelerations you want, and then you can go do a quick experiment like this just to see if CV is going to add anything or not, but it's probably not. And you can just turn it on, run the wizard with your final values just so that it has the correct data for your acceleration values. But it's probably not a big deal whether it's on or not. Okay, now I just want to quickly show how to use the wizards to set up CV mode. So you're going to go disable your machine, go to wizard, we're going to select MC CV tuning. This is the wizard. in my setup, I had some other versions of this. The MCCV is the latest version. That's the one you should use. So I was kind of explaining what it's doing in here. I didn't find this particularly useful, but the first thing you want to do on the next page is select which motors or axes you want it to calculate based on. So what it's doing is it's saying, hey, I'm going to go look at the acceleration settings you have in your Mach4 menu for these motors and use that and what it's going to do is whatever the worst case or lowest acceleration value is, that's what it's going to use in its calculations. So I did X and Y. You could use Z2, I suppose, if you're doing like 3D carving. It's probably using constant velocity mode, say between your X-axis, which is your raster direction, or can be your raster direction, and your Z-axis when it's going up and down. But I only did it for X and Y. Most people do. Then the next page is where you put that error tolerances. So this is that error between the corner, the exact corner of whatever vectors are drawn. So it's looking ahead and going, oh, I see a corner coming up. It's, in Mach4 has a look ahead of the, the next 20 lines of code or whatever. You can set that in your Mach4 menu. And so it's looking ahead and seeing, oh, I've got a 90-degree corner coming up, or a 179-degree corner coming up, or whatever. It's going to calculate based on this error, that this table that we're going to look at in a second. So I'm going to say 0.001. I'm going to leave it at the default. So 1,000th of an error. That's a very small value, especially for me. I'm a woodworker, so that's like nothing. And it's going to make those calculations based on that. So I say next, does some calculations, and now it says, well, if you get a next button, it's done. So I hit next, finish. So it's recalculated all that. And what it does is it stores that in the machine INI file. You can go look at it there, but they also have a wizard to look at it. So I'm going to select that wizard, which is called CV feed rate. And all this does is shows the table. Whoops. It shows the CV table here that it created. So we've got feed rate and blend radius, as I showed before, and you can see as the angle gets higher and higher, so basically it's getting to be more and more acute, the radius gets smaller and smaller, and the speed also gets smaller and smaller. So this angle 0 is basically a straight line, right? It's a 180-degree angle or straight line. And this angle 1 is 179 degrees. So almost a straight line. So the radius could be huge for that small error. It's almost it's an arc that's almost a parallel line to it, and it can go very fast. And as you get smaller, if we go to the 90-degree value, that is the squares that I've been using, you can see the 2.8 thousandth radius again that I had before, and now it's saying 9 inches per minute is the fastest it can whip around that corner with the acceleration settings and maintain the 1,000th of an inch error. And you can see, the more acute the angle gets, the smaller that radius gets and the smaller the speed is. So it all kind of makes sense. So this is the data that's created with that. And this is really just like an information one. Then if we go to configure and control, I'll show right up on the defaults page. Here's where you turn on exact stop or constant velocity mode. Again, I would recommend just leaving it on constant velocity. It doesn't seem, theoretically it helps, but again, from what I've seen on my particular machine and the acceleration settings I have, it really doesn't make any difference. If you had NEMA 23 configuration of an AVID machine and you had a really big heavy machine, you might find that you have to run at slower accelerations, but I kind of doubt that you'd even have to run those that slow to really need this mode. The other way you can always tell what mode you're in is if it says G61 or G64 down here. The machine, when it's first, or when Mach4 first comes up, it's going to say G61, which is exact stop mode. But when I enable, which I can't do offline here, there it goes. As soon as you enable it, it reads those menus and updates it. Now it says G64, so I know it's in constant velocity mode. So that's about all there is to say about constant velocity. I think it was possibly more useful. There's a really good video from CNC Nuts where he went over what CV mode looks like and stuff, but he didn't have an AVID machine. That looked like a home brewed machine with ball screws and stuff on it. So, you know, he had different capabilities on that machine. Probably had to run a lot slower acceleration so he didn't lose steps and stuff. But again, with the AVID machines and the big motors that are on them, you're really not going to ever have to run slow enough, even to reduce your vibration, to have CV mode do anything significant for you. So in summary, I've tested every different kind of tool path that I care about with these experiments to kind of dial in where is the best place to put my acceleration settings to reduce the vibration to where it doesn't degrade my laser marks, and that's kind of worst case. But it's also helping like my V-carve edge cleanliness. And then I also looked at the trade-offs in execution time there, and my conclusion, at least for my machine and the performance I'm getting and what I can tolerate as far as running the job slower and stuff, is that 15 inches per second squared is about the sweet spot for me, which is a lot lower than the 50 inches per second that the software package kind of comes set with, but it's much, much lower vibration. I also have, braced my machine up so that the table has more stiffness than the stock one. So other people without that, or with a bigger machine possibly and more weight, might find that even more reduction is necessary if they're trying to get the really good performance on something like a laser. But if they have a different table or different size machine, like a Desktop Pro, probably can run significantly faster without degradation, and it probably doesn't vibrate as much either because the gantry and everything is lighter. So it's all related. The vibration is related to the speed and the amount of mass you're moving around. So everybody's going to be a little bit different, and everybody's doing different kinds of jobs here. So this is why there's no right. I don't want to imply that 15 is the right answer for everybody. 15 is the right answer for me. But hopefully what I showed was how you can how these settings affect your performance, both your execution time performance and your vibration performance. And hopefully it'll help you kind of dial your machine in if you're having problems with your laser or V-carving, you want it to run a little smoother. And then in the end, hopefully I explained constant velocity mode well enough. Like I said, there's not a lot of information in Mach4's documentation or on the internet, but in the end, it turned out to be a lot less important in performance. In fact, not at all, from what I can tell. So I think, again, that's maybe not for AVID machines. It might be useful for other people, but not really for these. So if you have any questions, please put it down in the comment section. I'm always happy to answer questions. And if you like the video, please like it and subscribe. That always helps me out a little. Thank you very much.